Welcome to this session on the Gradle roadmap. So my name is Adam Murdoch. I'm CTO and co-founder of Gradle. So in this session, I want to look at the roadmap for the Gradle build tool. So I'm not going to look at build scans or build chip. And in particular, I want to look at a few features that we're working on to make Gradle go faster. So this has been a focus of the last few months, and we've made good progress. So the daemon is on by default now. That makes a huge difference to build speed. Build configuration is faster. Incremental build is a lot faster. Dependency resolution, test execution, IDE import, all of these things are much faster now. Even relative to the last few releases. But we feel that this is still a major pain point for a lot of teams. Particularly in domains such as the native domain, the Android domain. These teams are feeling particular pain. So we want to continue to focus on that over the next few months and the rest of the year. And the goal is really, ultimately, for all of the work that we're doing across all of the products, is to make developers more productive. So developers run Gradle many times a day in the IDE, on the command line. They've got their CI machines cranking away running Gradle. So making the build faster means better feedback from the CI pipeline. It means developers don't need to leave their flow to wait for the build to finish. And just generally, the software development process, the software delivery process is more efficient. So we're not just working on making Gradle faster. There's other aspects of developer efficiency that we want to address as well. So for example, with build scans, that gives you insight into what the build's doing and how it behaves. So yes, you can make the build faster using that information, but you can also make the build more stable and more reliable, which has a big impact on developer efficiency. And you can see how developers are using the build, and so you can make that interaction nicer. Another example is the Kotlin build scripts. So the goal there is to make the experience in the IDE much, much nicer when you're writing a Gradle build, when you're writing your build logic. So you can do refactorings and find usages and code inspections, content completion, all really nice stuff to make that development experience much nicer. But the priority is about making Gradle faster. So let's have a look at a bit more detail. So a really common pattern that teams use when they're building a large piece of software is to chop it up into smaller pieces, into modules, and then compose those modules into an application or publish those modules, and other teams can build applications with them. And this works really nice in Gradle. You can define a project for each module, have dependencies, import into the IDE, run tests, all that kind of stuff. It works really nicely. But there's another pattern that teams use when they've modularized their software to help decouple that software and make it more flexible and easy to change. And that pattern is to define an API for the module, so the public bits that you can use from outside the module, and an implementation piece, which is the internal stuff that you shouldn't use from outside the module. So that means it's easy to change things. You can change the implementation, and the API provides stability. So Gradle doesn't understand this pattern, so it can't do anything to help you. It can't validate that you're intentionally or unintentionally reaching across and using implementation details. It can't tell the tooling about that, so it can't help you with API documentation. It can't tell the IDE about that stuff, so it can't help you with things like code completion and so on, inspections. And there's also a performance implication. So when you're building something, when Gradle's compiling something against a particular module, it doesn't know which bits of the API, which classes of the API, which dependencies are part of the API. So it has to provide everything to the compiler, all of the classes and all of the dependencies. So that means next time you go and build that thing, Gradle, and you've changed an implementation, something in the implementation, so like a method body, maybe you've added an implementation class, maybe you've changed an implementation dependency. Gradle needs to go and recompile. Gradle will recompile that software that's using the module, even though it doesn't need to, because that consuming module isn't using any of the API. So the bytecode will be exactly the same. So Gradle's doing unnecessary work there. And this, of course, gets worse as the dependency graph gets deeper and deeper. So you've got a library using a library, using a library, using an application, and you've built all this stuff, and you change an implementation detail down here. That leaks all the way through, so Gradle recompiles everything. And also is a problem across binary dependencies. So when you change an implementation detail in your module, that problem leaks to other teams who are using your module. So this has a really big impact on incremental build. Gradle's doing a lot of work it doesn't need to do. So what we want to do is give you a simple way to say, here's the API of my Java module. So here are the classes that make up the API, and here are the implementations. Here are the classes that make up my API, and here are the dependencies that make up my API. Everything else is just the implementation detail. And then when Gradle goes to compile something, another module against that module, it can just provide the API classes and the API dependencies to the compiler. So the implementation is hidden. And so you're getting some validation there at compile time that you're not accidentally using things you shouldn't be. Gradle can tell the IDE about that sort of stuff. And Gradle doesn't need to recompile consuming modules when the API doesn't change. So if I've got an application using a library, I change some method body in the library, Gradle doesn't need to recompile the application because the signatures of the API haven't changed. So this is a super nice feature. It's what I'm doing here is I can describe the architecture of my software, the structure of it. And in return for that, the tooling gives me some good validation and assistance when I'm developing, and I get faster builds in return. So it's really nice. The pattern we're using here, or the model we're using here, is exactly the same as for Java 9 modules. So there's a nice migration story there. You can modularize your software without having to do a big bang migration to Java 9. So build scans can help out here as well. So they can show us things like, or we'll be able to show us things like which modules are defining an API, and so aren't leaking stuff and affecting incremental build, and those modules that aren't defining an API, and so do leak all their details, all their implementation dependencies, and blow out incremental build speed. So nice way to help you do this migration. So another feature we're working on is composite builds. So composite builds allow you to take multiple builds that are normally independent and separately life-cycled and compose them into a single logical build where Gradle then can build everything at once. So for example, I've got maybe an application that uses a library. I've got this library, it's got its own build. I build it, test it, release it separately, publish it up to a Maven repository. I have an application that uses that. I have an application that's got its own build. It uses that jar from the repository. So the workflow when I need to do a cross-cutting change is quite awkward. So I have to check out my library, make my changes, maybe change that library build so that it publishes locally. I have to check out my application build, maybe change that so it uses the local version of the library. Then I can make my changes. So lots of manual steps. There's friction there. It just makes it all a bit more awkward. So by using a composite build that takes the library and the application builds and composes them into a single build, Gradle replaces that binary dependency between the two projects with a local project dependency, or the equivalent of a project dependency. And then I can just tell Gradle, please test my application. It builds the library with my changes, makes a local jar, and then uses that local jar to build and test my application. This is a much nicer workflow there, much easier. And something that's super important here is I didn't have to change either of those builds to compose them. I just check out the library build, check out the application build, and say, Gradle, connect those together. So I don't have to change them. So super easy to start using this feature. So what's the performance story here? Why is this part of making Gradle faster? So there's two aspects to this. So firstly, the builds interact through dependencies and dependencies only. So the build logic for one build can't reach across and affect the configuration or the state of the other build. It can't configure things, can't read settings. Only interact through these dependencies and the outputs of the builds. So what that means is that Gradle can configure those builds in parallel, and it can build those things in parallel as well. It's only when we hit a dependency that Gradle needs to do some synchronization there, but otherwise everything can just run independently. So I can take a large monolithic build, I can bust it up into smaller pieces that make sense on their own. And of course, if I'm just building one of them, it's smaller, so it's faster. But then when I compose them all together again, it's faster because they're all being built and configured in parallel. So the second piece here is there's some interesting implications of just using dependencies between these builds. So I can take these builds and I can distribute them across multiple machines because they're only interacting through these outputs, through the dependencies. So composite builds can lead very naturally into a distributed build story. There's no reason why those builds have to be different builds. So let's say I have a native application that I'm building, and I build it on Windows and Linux and Mac OS. I could have a composite build that has an instance of the build on the Windows machine, building and testing the Windows executable, another instance of exactly the same build on the Linux machine, building and testing for Linux, and another instance of exactly the same build running on Mac OS. And I can compose those together and do Gradle test. My changes get built and tested on each of those machines and each of those platforms concurrently. So some really interesting things we can do there. So again, this is a really nice, really nice feature. It's making existing workflows a lot smoother. It's introducing new kinds of workflows that you can do. So for example, I can check out maybe a service I'm working on and some applications that use that service. I can have a composite build that checks my changes, builds and tests my service, and then runs the tests for these downstream consumers as well, all as a composite build before I push those changes up to CI. So interesting workflows, and then some really interesting options for making the builds faster. So let's look at some features or some changes that are just about making Gradle faster. So configuration time is the time between when you do Gradle something and when Gradle starts doing useful work, as in starts running tasks. So this is the time when Gradle's running build scripts and applying plugins and defining tasks and configuring tasks and calculating the task graph and so on. And this time this is just overhead. This is just a cost you pay every time you invoke Gradle. So if you're importing into the IDE, you're paying this cost, or synchronizing your IDE model, you're paying this cost. If you're running some tests, you're paying this cost. Even if you're doing Gradle help or Gradle tasks, you're paying this cost. So it has a huge impact on developer efficiency and also just even perceived speed of the build. So this is something really important that we want to really focus on and just make that smaller and smaller and smaller. And we've made good progress. So we've done lots of optimization of configuration time. And these have all been changes that have been transparent to your build logic. So you haven't needed to change anything in your build to use these improvements. You just upgrade to a new version of Gradle, and it's faster, which is nice. And we want to keep doing that. There's a few more optimizations we want to do in configuration time to make that faster. But there's also, what we also want to do is make some changes to how you structure, some very small changes to how you structure your build logic so that we can then make further improvements that otherwise wouldn't be possible. And the idea here is really to take a very similar kind of approach we're just looking at with composite builds, where the builds are independent from each other, and so we can do interesting things, and apply that to the projects within a multi-project build. So give you a simple way to say, the build logic for this project and the task for this project, they don't reach across and touch any of the state of any other projects in the build. They don't mutate anything, they don't read anything, they only have project dependencies. They only interact through the outputs of those projects. And then we can do the same sorts of things we were just talking about with composite builds. We can do that at the project level. So for example, if I say this project is decoupled or is isolated from the other projects in the build, I only need to configure that project when it's actually required for the build. So if I've got a 1,000 project build and I'm only working on a single project, right now Gradle configures all 1,000 projects, even though all that work is not required. It's just wasted time. So by decoupling your projects, by saying this project is isolated from the others, Gradle can just configure that and it can ignore the other projects in the build. So that, of course, means a much faster configuration time. But then, of course, because they're decoupled, we can configure these projects in parallel, and we can be running the tasks for these projects in parallel as well. And then, also, eventually, we can start moving those projects to other machines, start distributing them around. So because of backwards compatibility, if you don't say anything about your projects, we'll just assume that they are coupled together. We'll just do the existing behavior. We'll configure everything. We'll run things sequentially. If you do say these projects are decoupled, then we can do all this cool stuff for you. So the plan is also that build scans will help out here by showing you which projects, or can help you by showing what projects are coupled together and ideally how they're coupled together, so you can do something about that. And it can show you how well that parallelization is working, how effective it is or is not, so that you can do something about that as well. So dependency resolution has a huge impact on build speed because it's everywhere. So you think running a build script, we need to calculate the class path for that build script, which means a dependency resolve. You apply a plugin, we need to find the implementation and its runtime dependencies, or its runtime's class path. So that's a dependency resolve. So it's happening at configuration time. It's not just an execution time thing. You build your classes, need a compile class path, that's a resolve. Test classes, test class path, that's a resolve. Run your tests, that's a resolve. Run your application, that's a resolve. Do check style, that's a resolve. Need a check style implementation. And then if I'm building Android or native applications, things with lots of variants, I need to do that many, many times, once for each variant. So basically, almost every useful thing that Gradle does has some kind of dependency resolution involved. So making it faster is super important. And there's two things we want to do in particular. So first we want to do some smarter caching So Gradle does do some caching. There is lots of caching involved in dependency resolution, but it's very low level. So Gradle's remembering things like, oh, I got that jar from that repository and I downloaded it here. It's here on the file system and it has this metadata. Or I downloaded this POM from this repository and we parsed it and got this result. Here it is here. But every time Gradle does a resolve, it's still calculating the dependency graph. So it's calculating the actual graph and the versions of things that are actually required. And it's calculating the set of files to include in the result, so the actual files to include. And in general, that's very fast because it's sitting on top of this caching. But it still is work, and it can still add up. So if you have really large dependency graphs, if you have many, many, many projects, or many, many, many variants, there's lots of dependency graphs to resolve there. Or if you've got the same dependency graph in many locations. So if you're applying the same plugin to many projects, or using the same check style implementation in many projects, that's the same graph each time, and we're calculating it each time. So we want to do some smarter caching there. Introduce a higher level cache where we remember, here are the dependency declarations we took as input. Here are the repository definitions we took as input. We did our calculation. We got this dependency graph and this set of files. So just remember that fact. Next time we run the build, if those things haven't changed, just reuse the result. And we know from spiking and trying this out that this is actually this has a big impact on build speed. This can have a huge improvement. The problem is that caching, and particularly in dependency resolution, caching isn't always going to be applicable. You can't always reuse the result. So for example, a fresh checkout of a project. This is the first time I've built this thing. I don't have any result to reuse. Or if I'm running CI jobs on a CI agent where I'm blowing away the cache each time, there's nothing there to reuse. I have to recalculate all this stuff. Another example is where I've got a project with many dependencies that are changing frequently. Generally, I can't reuse the result when things are changing. So what we want to do there, in these situations where you can't reuse the dependency result from last time, is do the work of dependency resolution in parallel. So dependency resolution is really just a bunch of independent work that we just do sequentially now, so we can do that in parallel. So for example, if I have a dependency declaration on a particular library, Gradle has to go and find the right version of that library in a repository somewhere. It needs to download the POM, it needs ivy.xml, it needs to parse that, update the local cache. So it can be easily doing that stuff in parallel for each dependency declaration, and we just can gather up the results at the end. Another example is where we're calculating the files to include in the result, the artifact. For each of those, we go and look for, say, a jar in a repository, we download it, or maybe we check if it's changed. We update our local cache. So we can be doing that in parallel for each artifact. So there's lots of opportunities for making this work in parallel. So these kind of changes, these kind of improvements to dependency resolution will be transparent to your build logic. They won't require any change to your build logic. You just upgrade to a new version of Gradle and away it goes. So we want build scans to help out here as well, potentially, showing you what is being cached, what isn't being cached, and why it's not being cached, ideally. What is being resolved in parallel, and where the bottlenecks in dependency resolution are, so you can do something about that, or at least understand what's going on. So all the useful work that Gradle does is done by tasks. So compiling things, generating source, running tests, publishing things, deploying things, it's all done by tasks. So making task execution as efficient as possible is important if we're going to make Gradle super fast. And a task is really just a transformation that takes some inputs, so maybe some configuration or some settings, maybe some source files, and it does some work on those files and produces some outputs. And often, or almost always, these transformations are reproducible or reproducible enough that if you've already done the work for a given set of inputs, you can just reuse the outputs from last time. You don't need to do that work again. And so this is how incremental build works today. When Gradle goes to run a task, it looks at the inputs. If they haven't changed, and the outputs are still there and they haven't changed, just reuse those outputs. You don't need to redo all that work. You don't need to run that task. But again, this is just a kind of caching, and just as we saw with dependency resolution, this isn't always applicable. It doesn't always work. Fresh checkout, there's no outputs there to reuse. Running the build in a ephemeral CI agent, there's no result from last time, nothing to reuse. Switching between branches is another example where the outputs can't be reused. The other thing is that there are other people on my team doing exactly the same work that I'm doing. They're running the same tasks. There's CI agents out there running the same tasks, doing the same work. So by having everyone do the same work, it's wasted work. So we've been working on a distributed cache of these task outputs. So now instead of just looking at have I built the outputs locally for these inputs, I can look in this cache, or Gradle can look in this cache and go, has anyone on my team or has anyone in my organization or have any of our CI agents built these outputs for these inputs? If so, just get them from the cache, copy them into the output location, and don't run the task. So we want this to be really easy to start using. So the plan is that a plugin author will change their task implementation to add some extra metadata, or tweak the existing metadata actually, so that the task is now usable by the output cache. They'll publish a new version of their plugin. You can change your build to point at that new version, point Gradle at your cache instance, and it'll just start working. So you don't need to change your build logic. It's nice and easy to start using this capability. And then when we do need to actually run a task, we want to run as many of them in parallel as we possibly can. So at the moment, Gradle doesn't run tasks in parallel, at least by default, because it has no idea what that task whether that task implementation is reaching up to the project state and mutating things or reading things. So it doesn't. So Gradle doesn't run them in parallel. So we don't get the interference between those tasks that are mutating the project state. But what we want to do there is similar to what we're doing with composite builds and these decoupled projects, is give you a way to say the implementation of this task doesn't reach up and touch the project state at all. It doesn't read anything, it doesn't write anything. It only reads from its inputs and it only writes to its outputs. And that means we can run those tasks in parallel because we know what those inputs are, we know what those outputs are. Again, we want this to be low impact as far as starting to use this goes. So again, a plugin author will change their task implementations to say, yes, this task implementation does not touch the project state at all. It only reads from its inputs. It only writes to its outputs. They publish a new version of their plugin. You start using it in your build, and those tasks will just start running in parallel. So you don't need to change your build logic there at all to start using that, or won't need to, I should say. So this is super important for things like when you're building native software, when you're building Android software, where you've got lots of variants in the same project. But each variant can be built independently. So you can run the tasks. So to be able to run the tasks for each of those variants in parallel, have a nice impact on build speed. So there are things that build scans can help out with here. They can show you, or we'll be able to show you what is being cached, what task outputs are being cached, what isn't being cached, why things are out of date, which tasks are running in parallel, which tasks are not, which task implementations are cache enabled, which ones are parallel, safe. To give you insight into how to improve that, what still needs migrating, what dependencies need to be tweaked, and so on. So just to recap, so we've really seen the same pattern stamped out a few times here, where we decouple things by hiding some of the detail or even all of the detail about something so that we can do things more quickly. For example, hide the implementation detail of a module so that we don't need to recompile things when the APIs don't change. Decouple project state, the state of projects from each other so that we only need to configure the projects that are actually required. So we want to reuse work that's already been done. So don't build task outputs if someone else has already done so. Don't recalculate a dependency graph if you already have the answer. And for the work you do need to do it in parallel and later distribute that across multiple machines. So, any questions? Yes.
Yeah, a number of the points you're making, I remember from last year with the new model, what some of the promises of the new model were to help identify, obviously, these things to accomplish these tasks. I hear that from what you were saying, there's a bit of a, if you will, a backboard where we'll be able to bring this in without the model. Can you elaborate on that?
That's exactly the idea. So we talked about, yeah, exactly. Last year we talked about this kind of stuff in the context of the software model. And so we did a lot of work on that during the year and found some nice things. Like some of these things are quite effective. The thing we have with the software model is until you migrate to the software model, you don't get any of that goodness. And importantly, until all of the plugins that you use are using the software model, you don't get any of that goodness. So we wanted to basically take that stuff and backport it so that it's available now in the current model so you can just start using it. And there's another important aspect there is it's actually starting to merge the two. So the worlds are starting to come together there. So API definitions versus implementation are the same. Decoupling things and putting boundaries around things, it's the same approach in both spaces. So yeah, definitely that's exactly the idea. Start backporting some of the goodness because we want people to start using it as soon as possible.
When is that available?
So this is all, and again, this is it's a slightly different approach. So the software model is really solve the universe, and then we can all start enjoying that. This is a much more incremental approach. So we're doing each of these features essentially independently. So we've started work on so composite builds. You've already seen that's happening. The task cache is happening now. Some of the things like dependency resolution improvements and configuration time improvements, they're happening in the next months. So we're sort of talking this by the end of this year kind of time frame for a lot of this stuff. The distributed stuff is more off in the distance, but the idea there is really to show, look, here is some very exciting potential we have here with composite builds and decoupling things.
As I understood, composite builds have to play nicely with jigsaw project. So it means that I can, let's say, put in the modules, cohesive code, create a build, and say it's my model, and I have some microservice I built with Gradle, and I still try to use modules, and I look at here, it's supposed to work nicely. If I need to change my model, it's had to be built with composite modules if I try to rebuild my microservice, right?
You don't have to. So the idea is whatever you can do now, you can continue to do now. There's no have to compose these things. So if they do have separate workflows, separate life cycles, and you continue to just do that as you do now, the idea with the composite builds is that it makes it easier to do these workflows. Because the reality is these things do have dependencies between each other, and you do sometimes need to do cross-cutting work, and you definitely need to be able to verify that your downstream dependencies aren't broken. So this is an easier way to do that, but you can do this now with Gradle already. It's just your responsibility to take care of the wiring and the IDE import and all that kind of stuff, whereas with Composite build, it just makes that easier. Gradle takes care of the wiring and the IDE import and things like that. So the intention is to take some of these workflows that are either very difficult or awkward and just make them smoother. But it's not just making them smoother because of those performance implications as well. There's also, it's starting to put some structure around, or decompose large things into small things, and then we can do interesting things with those small pieces rather than having to do everything all the time with a giant monolith. So there's two aspects to it. There's two motivations for it. Any more questions? All right, thank you very much.